My name is Samson. You can call me pretty much anything. I'll respond to anything, particularly if it's a dinner bell or a lunch bell. So you can call me whatever you like. So we always like to kick off the show by saying, welcome to the space economy, your destination for the business of space. George is standing upright. He's all prim and proper. I'm in Florida. I've got my Florida attire on because I'm going to the beach in a moment. But since Manuel just joined us and Marcus has been here, I sort of want to just jump into what is this magnetoplasmadynamics, but I'm going to pitch it over to George first because he's like, we got to talk to these guys about the awesome technology that they're bringing.
So when I was doing our pre-read, when we were looking to invite you guys on, I was looking at all of the fantastic work you've been doing around the heat shields. And I guess the easiest way to put it is I never understood just how important they are and really just how basic the current designs are. And so that's where you guys are coming in. You're applying new technology to try to make these heat shields less bulky, because obviously they are a lot of weight when it comes to the capsules and the spaceships. So can you talk a little bit about that and how you're providing a solution to this?
I'm gonna pass this answer to my colleague Marcus, since he's one of the most knowledgeable on the topic. So Marcus.
Yeah, very good question, George, and it is a big problem. The solution that we bring, not just for that application, but for several, is the use of superconductors. And I have one here in my hand, and this is a really thin tape, which you might be able to see. This can carry 800 amps of current, and that, for non-technical people, is a huge amount in such a small tape. And you're right, it is an issue with these heat shields. Depending on which mission you look at, they can be as much as 35% of the mass of your capsule, and that's when you're sending stuff to Mars. That's a lot of money, which is just being used to protect the spacecraft. With the superconductor, you can make a shielding without using materials, and you do this by winding this into a coil, putting a load of electricity through it, and that generates a magnetic field. And it's like sci-fi, but now becoming a reality. The magnetic field literally shields the spacecraft. It pushes away the hot gases and the hot plasma from the edge of the spacecraft, and in doing so, there's not so much heating. And the other problem it solves is that it allows radio communications to take place. So you know,
Marcus, let me interrupt and ask you two highly technical questions. Number one, what's the name of your business again?
Neutron Star Systems.
Neutron Star Systems just said that they're building the technology so that when Jean-Luc Picard or someone else says shields up, someone hits a button. Did I interpret that correctly?
Yeah, damn right. That's one of our hashtags, is shields up. We use that on some of the social media.
Okay, because I saw this thin little strip, and I was like, that's interesting. But then when you explain, you put it in a coil, you hit the button, you gotta imagine that there's an electron-magnetic field over. So the Earth has one, that's where we get the auroras borealis, that feel like at the poles. So it's a similar concept.
Yeah, it's a similar concept. It's the shielding. So yeah, like the Earth magnetic field shields the Earth from the sun and the plasma coming from the sun, our magnetic field shields the spacecraft from the plasma which comes from the gas in the atmosphere. Because when you're coming from space, you're going several kilometers a second. I mean, things in space move so fast. As soon as they hit that gas in the atmosphere, the whole thing heats up and it gets so hot it ionizes and becomes a plasma. And that's what you need to shield against. And that happens not only on Earth, but also at Mars. It's the same problem.
I love it. I know George has some highly technical economic questions, but you just told me that when the spacecraft comes in and it's hitting it's exciting the air molecules and they go, and they get plasma all around, that you hit the shields up button and the shield pop up, this electromagnetic field pops up, and it keeps the plasma, let's say it keeps it here from the spaceship. And by the way, you can get one of these spaceships pretty much anywhere. This isn't rated for space, by the way.
Yeah, the technical denomination for that is plasma boundary layer displacement.
Repeat that for me one more time.
Plasma boundary layer displacement.
Plasma boundary layer displacement.
Boundary layer displacement. And it's not other thing that exactly what you described. The electromagnetic field is so high that you basically increase the distance in which the heat flux impact the spacecraft. And therefore, you can have thermal protection systems that are not so heavy. You can have more payload in your spacecraft. You can also, and this is really important, you can change the geometry of your spacecraft. And this is something that that today capsules are made in a way that thermodynamically they can re-enter without burning. Okay, and that's why they have the form, etc. But by having such a re-entry shielding technology, you can use other more suitable re-entry geometries for the fuselage of your spacecraft, that are more similar to hypersonic planes architectures.
So that's a good lead in. I was going to ask about where the applications were for this for hypersonic vehicles and hypersonic equipment, because that's obviously something that's getting a lot of attention now. Is it similar in the way that you would be able to use the same technology for the benefit of hypersonic equipment?
Marcus, or yeah.
It's something we don't know for sure, but certainly it's something we're starting to explore now, especially in the framework of this program we're doing at the Catalyst Accelerator. There's a lot of discussion on hypersonics. It's quite a big area now at the moment, especially in the US. And when you look at the same speed you're going at and you're in the same environment of being in the atmosphere, then I think certainly there could be an application for it. It's just a case of making the trade-offs and seeing if it makes sense.
Excellent. You mentioned something else there. You mentioned the Accelerator. I also remember reading about some various grant supports you received, right? Can you talk a little bit about those so we can understand what the economics of the business has been to this point and what the accelerators and grants and recognition you guys have received?
May I take that one, Marcus? Yeah. They might look disarticulated and not interconnected, but they are. So the grants we have is one grant for the development of a demonstrator for a re-entry shield based on a superconductor appliance. It's the same coil with the same protection, etc. The other grant is for a superconducting harness and or a joint or a cable. So this is another application of superconductors. Our business is the development, production, and sales of superconductor-based spacecraft systems and subsystems. So if you look at the system architecture on a mission, you will always have propulsion, you will have power management and distribution, you will have potentially re-entry if you want to send a spacecraft to Mars and then re-enter there. And if you're sending it with humans, you will need radiation shielding. All of these functionalities can be enabled and can be solved by the use of high-temperature superconductor applications, mostly electromagnetic coils. So the grant from the EU is for a re-entry. The grant from ESA, or the contract with ESA, is for the production of a superconducting harness. And the accelerator grants or programs are more into the, fine-tuning the user cases, fine-tuning the customer base, our business plan, and all these sort of things.
I love it. I love it. So here at Space Economy, we're talking to Manuel and Marcus from NeutronStar.Systems. You can look them up on the internet at NeutronStar.Systems. And I'm having sci-fi moments all over the place because I love this idea of having shields up. So I have a highly technical question for you gentlemen, because we talked about reentry. I got my reentry vehicle, right? Plasma, all that good stuff. Sometimes there's just satellites in orbit, and then there's space debris. Can you put this electronic coil on your satellite so that it repels or prevents space debris from coming in there? Or does it only work with plasma? It's a highly technical question because we talk a lot about space debris.
Go into the thrust vectoring and the throttlability, explain.
What I've done is I've brought up a really fun background, which is our thruster application of the superconductors. So no, you can't use the shields to, let's say, bounce a piece of space debris away because it's matter. What you can do is use a superconductor on a propulsion system to make it more scalable, to make it more throttleable, and actually to increase the thrust. And with that propulsion system, you can perform the collision avoidance maneuver to miss the space debris. And this is really important because spacecraft have a lot of different needs from their propulsion. Sometimes they need very high efficiency so that they keep in orbit, but sometimes they need a high thrust if they need to make an emergency maneuver. And most of existing systems today can only do one or the other, but the thruster that we're building will be able to do both. So it has a solution to that problem as well.
So whereas it cannot stop my physical object from impacting my satellite or station or space station, your thruster will help the space station gain altitude or move to avoid said object that's coming, correct?
Correct.
Excellent. I went to public school in Texas, so I have to use like little things to make things make sense. But no, that's still really cool because I want to say now that thruster systems, some of them are chemical, some of them are air-based. But this, because really my question is, what's the lifespan of this electromagnetic coils? Like, how much battery or juice does it require to operate?
Well, the beautiful thing about superconductors is they have zero resistance. And that means as soon as you put a current into the coil, it's going to stay there for even thousands of years. Any resistance that's there is so small that it just doesn't go away. All you need to do is keep it cool. So you have a power source for a cooling system, and these are cooling systems which are used already on spacecraft for science missions and for imaging equipment. And we just need to adapt that to work with the coil. And then you load it with electricity and it's loaded. You don't need a battery to keep it running, which is a really nice part.
So Marcus, you're blowing my mind. NeutronStar.Systems is blowing my mind. When you load your coil, this gets to be my coil, right? So when you load your coil, when you use the energy that's inside this coil, can this coil be recharged? Can it be reused?
So you're actually using the energy on what we call the discharge of the thruster, which is this part here. You're putting the energy into your fuel. And the coil, if you didn't have the coil, it would just kind of sit there and you'd get some thrust, but not very much. But what the coil does is it makes the magnetic field, which accelerates that entire plasma and throws it out of the thruster at a huge velocity. So the coil itself, you don't need to keep recharging it. If you do drain it, which you can do, and that has certain applications, you can easily recharge it. But from an operational point of view, you only need to provide the thruster, provide the energy into the fuel, not into the coil.
That's awesome.
I had a follow-up right there. So when we're talking about superconductors, it makes me put on my my other hat. So it makes me think about rare earth minerals. And I know that a lot of superconductors rely on rare earths. And I believe it's barium and boron both have, when combined with rare earths, have these superconductive properties. Does your system, do your coils rely on rare earths? And if so, is there a supply demand concern there or a price concern there because of its reliance on rare earths?
I'll go on that one. Yes, we're working with second generation high temperature superconductors. Okay, that's very important to distinguish. So these ones can be Repcotase or Ipcotase. Both of them use rare earth materials, mostly coming from China, for their production. However, I mean, this percentage of material in the superconductor, you can talk about doping with, you know, very, very small ppm kind of things. So we don't see any constraint in the supply chain of this type of material, mostly because you have large superconductor producers in the United States, like Superpower or American Superconductors. You have Sunam in South Korea. You have Fujikura in Japan, Shanghai Superconductors, etc. The beauty of high-temperature superconductors nowadays is that they have become a type of off-the-shelf product. So they don't have the prices of an off-the-shelf product yet, because you must distinguish that. But they are commercially available, and you can find them, as Marcus showed you, in tapes of 12 millimeter width, 4 millimeters, 2 millimeters. I mean, and you can find them in wafers that can be used for ultra high frequency antennas, or for sensors, or for electromagnetic sensors in submarines, for the permit systems, for rail guns. You can use superconductors in a lot of really interesting applications. And the beauty of that is always the same. There where you need power, there where you need a high power density, where you really need to deal with hundreds of amps and so on, then superconductors becomes an ideal material or shoes.
Awesome. Manuel, Marcus, you NeutronStar.Systems is blowing my mind. I'm going to let George ask some really boring economic pricing questions in a moment. But I just want to say, I wrote down 3 things that I didn't think I was going to say today. One was plasma boundary layer displacement. I didn't actually know what that was. I didn't think of that. But I'm gonna be like, that could be a seed key for some blockchain stuff. So I'm going to remember that, do some research on it. 2, doping rare earth minerals. That's such an interesting concept, the way that you say that. I was like, dope in rare earth minerals. It sounds so interesting, but I think I get what you're saying. And the last thing, then I'll turn it over to George to ask you some boring business and economic questions, like how do you guys make money? Rail guns. I absolutely love the idea of a tungsten magnesium hard ball object being propelled super fast so that it can build up kinetic energy and hit something. We don't want to militarize space necessarily, but I'm thinking that it's a very interesting application because there's probably so many other things you can do with a railgun other than just launch bullets or projectiles really fast.
You can launch spacecraft from the moon. You don't have the gravity issues that you have here. Railguns are used here, especially in France. There is this institute, Saint Louis Institute, that is doing research on railguns for the navies. And you know, if your vessel got into between a railgun, you know, you lost it. You know, that will go over your panzer, etc. It will just go through.
So
the same you can use with a spacecraft on the moon. You can launch a small spacecraft with a railgun system, with a rail from the moon. And this is something that we are not inventing. This is something that has been around since the 90s. Okay, and by the way, NASA was the one who came across with this sort of concepts. We just recycled them, if you want to call it like that. And we just recycled them because at the end of the day, we just realized that the space industry missed superconductors a little bit out of sight, you see. So it's kind of like they forgot they were there, developing, you know, increasing, etc. And they have been already more than 30 years that they have been around. So now they are commercialized, and I think you can do a lot of things with them in space.
So I'm going to turn this over to George, but if you're looking for a railgun for whatever purposes, launch spaceships, shoot projectiles really fast, reach out to Manuel, NeutronStar.Systems. He'll hook you up with the railgun. Maybe you put it on the moon, maybe you don't. So George, for the folks listening to the space economy, let's talk about some of the economics. We have to mention at least one or two figures, otherwise someone will yell at us like, why did you talk to Manuel and Marcus about plasma boundary layer displacement if you didn't say how much does it cost or how much money they could make in the space economy? So George, ask us hard questions.
Sure. So I was thinking about one of the topics that might be related here, and if not, just bring me back on track. But these type of thrusters that you're describing, they're alternatives to argon, and so are these the type of thrusters that we could see on the next generation of Voyager probes? There's a recent press release about how Voyager was, how far it was from the Earth, 156 annuals, and so I was thinking about this. Are these the types of long charge materials like you described, where they get charged one time and then they just have this, great cycling rate? Would these be used potentially on deeper space exploration probes?
Yes, but that's not our primarily market objective. We are at near term. You see. We see the use of superconductors for geocom platforms, and mostly for platforms that allows encrypted and secure communication, multi-domain and multinational level. Basically, because with superconductors you can extend the power of your satellite and the communications transmission capability. Also the onboard onboard computing capability, and also by keeping the same or even a lower weight and volume. And this is something that is particularly interesting because you can launch a spacecraft that is going to be weighing 1 ton, 1.5 ton, but can deliver the same performance of a spacecraft that is 6 tons of weight. Just because the old geocommunication satellite platforms were using, large spacecraft. They were propelled with chemical propulsion. 2/3 of the mass will be propellant. So that's, for example, where we see, a point of entry. Marcus, you have probably another point of entry, or you say?
Yeah, just we have a lot of use cases for sure. Essentially anything where you need higher demand propulsion than what currently exists, and for higher powers, that means both high thrust and high efficiency. The only way you can get that is with high power electric propulsion, and in that regime, we really believe we have the most competitive product. And some examples are, for example, on-orbit servicing activities. That's what we're now working out in the Accelerator. And also, did you mention the space weather?
No, I didn't.
This is one of the big things we're also focusing on, using our thruster to propel and navigate satellites for monitoring the sun's behavior in order to improve solar weather forecasting times, because this has been identified as a significant need by the NOAA and other people in the US government.
Excellent.
Love it.
And so for these various use cases, I'm hearing use cases where ESA and NASA obviously are going to have quite a bit of interest. Where do you see, or do you see interest coming from non-national space agencies potentially for this technology?
If I may, mostly on the new space area for on-orbit servicing, capabilities such as refueling or orbit racing, or satellite maintenance. We see there a lot of companies for which we think we can increase and double the performance of that they can deliver. That's a really interesting one. And also the likes of Blue Origin or SpaceX, since they are quite engaged on transfers from the Earth to the Moon, and especially when it's related to cargo transfers, where you don't need to go fast through the Van Allen belt cosmic radiation area. You can use electric propulsion to save a lot of money. To give you an example, if you run a LEO to Moon cargo transfer of 27 tons with chemical propulsion, you will need for that 1.5 billion. If you run the same amount from LEO to Moon with electric propulsion, and our thruster, you will need only 200 million.
Whoa, we're gonna repeat that. We're gonna repeat that. With the current tech, chemical propulsion, you're saying it's gonna cost 1.5 billion with a B, so 1,500 million. And with your tech, what was the number again?
200 million.
200 million. That is huge.
You can say 400 million, and you and I can split the profit of that last 200 million.
So,
yeah, say 400. We'll figure out.
Yeah, we can. That's a good one. You see, guys. I mean, the savings on cargo transfers to Moon is on the order of the billions. If you multiply that for a 10 years operations with several missions, 1 on 4, you can save up to 7.5 billion in 10 years. Just like this. So, of course, you will ask, why is it that you are not just sitting at the top 500 fortune and you are not known from everybody?
That was the follow-on question.
Yeah, well, I tell you one thing, to kill or to beat 27, 30 years of legacy technologies and fly heritage is quite difficult. Remember, this technology of magnetoplasmadynamic was something that it's around since the 60s. And the Germans and the Americans started this. But then, since it was suitable for high-powered operations and they didn't have superconductors ready at that time, they need to look for an alternative solution. That solution is not the most sustainable, you see? And now we're trying to say, hey, before you engage on Artemis programs with Hall effect thruster technology, you should look at our technology because we're gonna save you a couple of hundred of millions. But that's the kind of paradigm change that we are trying to achieve. I know it's ambitious, but Marcus and myself, we're quite persistent.
No entrepreneur showed up without at least a spoonful of ambition. So I think you're well positioned.
So I just want to say thank you for joining us here on the Space Economy, your destination for the business space. And if you're still listening and watching, NeutronStar.Systems is Marcus and Manuel's website, because if you're still listening, you heard where you're currently spending 1.5 billion for the low cost of 500 million. They can make that possible for you. Yeah, we definitely share. This is where the 500 million comes in, because I was trying to think of, because some of our audience, they're not technical, but they're policymakers. And I was like, how do I explain this to everyone? Like the importance of the plasma boundary layer displacement, like why that's so important. And so I was like, you guys are sort of like windshield wipers for cars. And I'll explain why, because you're really a safety feature. Because if you put whatever your spaceship happens to be, if it's going to re-enter, well, you don't want it to break apart. You actually need that plasma boundary layer displacement to help protect this asset, the humans inside of it, and prevent space debris from happening. And so in many instances, you're really a safety feature. And so I could see where the requirement is, regardless of what space agency, is that you have this technology on board, 1, to protect the humans, 2, to protect the property, and 3, to help mitigate space debris. So I love what you guys are doing at NeutronStar.Systems. And again, for right now, 1.5 billion, low cost of 500 million, they can make your magic happen too. So that's it for me from the space economy perspective. I think we should wrap here so we can talk some real big numbers about, how do you guys take this to the next step? What is your journey to the next step? And of course, encourage the listeners and the viewers to follow you guys. So I'm going to ask Marcus and Manuel, if you can very briefly, just tell folks how do they find you to learn more about your awesomeness?
Well, we're in Germany and we're quite active on social media, especially Twitter, LinkedIn. We have a Facebook page, or just simply give us a call through our website.
Also invite you to check out the website for the project of the re-entry shielding. This is meest.eu, meest.eu. Please check it out. Very cool website, and you'll find out a lot more about that cool plasma boundary layer displacement.
Awesome, awesome. So there you've heard it from the horse's mouth, from the, not horse's mouth, from the geniuses' mouth themselves. And remember, for only $500 million this year only, can they help you make that happen? George, say goodbye to everybody.
We're in the need of someone with marketing knowledge, Samson. We might just
We'll do some of that offline, but we'll see everybody else in the next orbit.
Bye-bye.
Thank you a lot, guys.
Bye.
Thank you for the interview. Have a good day.